Okay, so I'll just, before I go to the practical session, I'll just learn. No, yes, okay. We'll start with an application, and as I said, it's a transformer-based one, so we said we work on visual question answering, where you take an image and you take a question. We use as a baseline model this LXMF model. One funny thing which I didn't talk about is that these things here are trained in a mixed way. First way is supervised. So this model here, where is my pointer? Good. So this model here, as I said, takes input images and questions and encodes them, and at some point provides an output here. And this output here, currently, it's not something I think is the future, but for the moment we do classification. So basically we take these thousands of possible answers, like yes, no, a little bit, whatever, left, right. They are transformed into classes, and we take the decision here as classification over the classes, over the answer classes. So at some point, I think this needs to be made a little bit richer, but for the moment, the community sticks to this classification version. The funny thing is, if you do it this way, and this is where big data and large scale machine learning comes into play. If you do it this way, then you need a couple of hundreds of thousands, millions or more data items. So meaning you need pairs of images and questions and annotated answer. This is a lot of effort. Obviously, this is done through crowdsourcing. So basically the academic or industrial teams put images and questions on, now they put images, basically what they do, they put images on the web, on Amazon Mechanical Turk, and ask human users, which are horribly underpaid, to provide possible questions and possible answers. So we have a couple of 100,000 up to millions of questions, but it's still not enough. So these reasoning functions here are really, really complex. So just imagine, again, did I leave the door open? Did I leave the lights on? So just imagine the sheer possible reasoning functions you need, and you need to cover lots of different areas. And so the amount of data is tremendous. And even crowdsourcing does not get us there. So what people do is self-supervised learning. What does self-supervised learning mean? So instead of just minimizing the error on the answer, we provide what is called auxiliary tasks. So there are specific additional output heads, predictors here. These predictors solve other tasks, and these other tasks are not necessary for deployment. So when this thing is deployed, these tasks, these heads here, are just cut away and not used. But during training, minimizing error on this additional task is very powerful. I'll give you an explanation for translation, where it's easier. Translation obviously means that you translate from one language to the next. So for example, you translate from French to English. And when you do that, you need large amounts of aligned sentences. So you take Anna Karenina, War and Peace, whatever book, you have lots of examples, but you need to align the sentences, right? Which sentence corresponds to what sentence? So it's actually not that easy to get, even for translation, lots of training data. And training only on translations is kind of ambiguous, because there can be multiple translations for each sentence. So what people do is, this is called the so-called BERT training, B-E-R-T, BERT training, new additional losses. I'll give you an example. It's very easy to find text which is not aligned, so monolingual. We have billions of books. And what you can do is you can take, for example, pairs of consecutive sentences in books, and you can look at them. These pairs of consecutive sentences, they are meaningful, right? I mean, you understand that they follow each other. There can't be any possible sentence pair. There needs to be some consecutive meaning. And what models do is you present them with billions, trillions of pairs of sentences. Some of them follow each other in text, Others do not. They are from different books or from the same book but far away. And the model needs to predict whether this is the case. Do the sentences follow each other or do they not? Two things. First of all, it's extremely easy to get annotated training data because you take literally all books which exist and you can just take consecutive sentences. That's very easy to do. Second thing, learning this task is very highly correlated to translation, or at least to understanding language, because in order to find out whether two consecutive sentences or whether two sentences can be consecutive in a text, you need to know what they mean. You need to have an understanding of their semantic meaning. So this is what is done. There are lots of different kinds of losses. For example, masking words and predicting them. What is missing in this sentence? So there are a dozen or so different auxiliary tasks, and we train them. And this is really the thing which makes transformers work. Without these auxiliary tasks, transformers basically, they don't work so well. So we have worked on this VQA application with Orange. This is mostly the work of my student Corentin in multiple ways. So first of all, we started to work on reasoning versus biases. So how do these models actually work? We worked a lot on transfer learning and how can we visualize the internal meaning of these models. We worked on alignment. Can we weakly supervise alignment between vision and language? And lately, this is not yet accepted. So this is a LIRIS submission. Can we supervise how this reasoning is actually performed? So I will only give a couple of, I can't present all these different papers. I'll just give you a couple of examples. So what you see here is an input pair. So we have this image here and a question, what is on the wall? Obviously, the answer is a star, right? Because the star is on the wall. Now, this is something funny because the star is not the random answer you would get in any example when you think what is on the wall. If you just look at what are the most probable answers you could have on this question without concentrating on a specific example, well, the most highly probable answers would be like painting, mirror, or something like that. And what we did is exactly that. So we evaluated how the relationship between the outputs of VQA models with respect to biases, statistical biases, which could be used by these models to answer. So we took the 44,000 question groups. What is a question group? A question group is not a question, it's a type of question. So what is on the wall or what is on is one of the groups. Okay, so for one of the most well-known VQA data sets, there are 44,000 annotated question groups. And for each question group, we check what are the answer distributions. And for the group object on the wall, well, some questions are highly frequent and others are not. And the most highly frequent ones are, and that's not surprising, picture, mirror, painting, etc. Star is here. Well, it's not very likely, right? So what we did is we checked, well, what are the answers of standard models? So for example, all these are state-of-the-art models in VQA, and lots of them are actually highly biased with respect to frequent groups. So this kind of indicates that they do not really reason. They don't learn reasoning. They exploit dataset bias. It's not the picture I paint is a little bit dire. There is lots of reasoning going on actually, but it's not exclusively well-formed reasoning. Finally, this LSTM model here, it's a recurrent network which doesn't use the English. It does not use the image. It's only using the question. So by definition, it cannot correctly reason. It can only exploit biases, and it will predict mirror. So what we did is in this paper here, where we propose a new benchmark, we propose new metrics, we calibrated the metrics. So we downgraded models and forced them to perform data set bias exploitation. We calibrated, we showed that our new metrics measured that biases. And what you see here is a couple of standard models from the state of the art. and what the performance is with respect to the frequency of the answers. So these are the most frequent answers here. No, sorry, these are the most frequent answers here, and these are the least frequent answers here. So on the most frequent answers, the models actually don't perform very well, right? So this means that lots of the state of the art actually is based on bias exploitation. Apart from this model here, what is this model here? It's a funny model. It uses ground truth objects. So this model here, when I go back to my slides, here I have an object detector. And in my object detector, I detect objects and they're represented by some kind of feature vector. If I replace this here by human annotation, and I'll just say, okay, humans tell me what objects are in the scene, and there is no uncertainty in my visual representation here. Well, then well, the problem is still quite strong, right? It's quite difficult because still the model still needs to understand the language. So we don't help him with this. So the model still needs to understand the language. It still needs to associate words with objects. It needs still to understand spatial logical reasoning. All this still needs to be done. It's just that there is no uncertainty in vision. All the objects which are necessary are there, right? Which is not necessarily the case with an object detector. Sometimes necessarily objects are not found. And well, if you work with this, then the model is actually quite good. We're almost at 100% here. So reasoning, high-level reasoning can be learned. The bottleneck is actually vision. So this was found by one of my students called Duncan Wadek, who is writing on his thesis right now. He's pretty soon on the market. And we provided a couple of things. So Oracle transfer, for example, this is the second paper which came out this year, where in this paper we showed that actually learning reasoning on this Oracle kind of model, so on perfect input, and then fine-tuning it on noisy data can actually work and boost performance. This is only one part of the paper. Most of this paper is actually concentrated on a deep analysis of the different transformer heads, what their functions are, what kind of things they learn, how we can visualize that. This was in collaboration with Theo Jonet, another student in my group, which are co-supervised with Romain Vimou. And Theo's thesis is on explainability in machine learning and data visualization. So Romain is a specialist in data viz. And we have actually a third paper where, so in this paper we do a data set-wise statistics. So this is a statistical evaluation, and all the explainable results are on data set-wise statistics. But we also dove deeply into an instant-based analysis. That's what I want to check right now. So this is a paper which has been conditionally accepted to Viz. I'll show you how this works. So I'll just, I'll need to share my screen. 1 second, because I'll prefer show you this tool on my computer. So this tool is available on the web. VQA, LIRIS, CNRS. It's a data visualization tool. It does real-time performance, so it takes a little bit of time because there are huge models. So these are huge models which need to be loaded, and the answer is not pre-computed. So basically, at each interaction, you calculate the forward pass. So here it is. So what you see here is you can perform real-time VQA on an example. So what do we have here? We have an image here, and we have a question up there. What is the mailbox made of? And what we see here is the transformer structure itself. So what you see here is the language-only transformer. So what you see is these boxes here are 4 different heads of 1 layer, right? So each box here, each small square is a transformer head. When I click at it, I can see here the attention distribution. And these are the same. Now these are different heads. Then I have layers here. This is the second layer, which has again 4 heads. The third layer, which has again 4 heads, fifth, etc., etc. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 layers. Then we have the vision model here. And here you have the cross transformer. So the cross modality transformer is a transformer which handles attention, cross attention. So from either from vision to language here, or from language to vision. And you can see that when you click on the language only, you see here the words and the words. So here, for example, here see which, let me get you this one here. Up. This means what is the attention from the word sidewalk to, for example, sidewalk, right? So that diagonal is attention to itself, and off diagonal is, so we have a normalization over the line. So over a single row here, the values are normalized with a softmax and they sum to 1. In the cross attention layer, for example, what you can find is, I'll take the Oracle model, it's easier to check. So Oracle model, in the Oracle model, the vision here, the vision part, I'll take another image which is a little bit better. Up. What animals are in this picture, for example? So in the language to vision module, you find, for example, here you find all the different objects in the image, okay? And here you find the words, okay? And here, for example, the word, the object bird here has been correctly assigned to animal, right? So the transformer, just through learning, has found out that the object bird here corresponds to animal. And I remind you that this is not supervised. So during training, we have no supervision for this, right? Supervision goes over either the answer class or through the self-supervised losses I just described a couple of minutes ago. But at no point we have supervision on this correspondence here. This kind of correspondence is learned. The second thing is, not all these different heads will learn very simple assignments between what word corresponds mostly to what object, right? Because all these heads here learn much more difficult and much more strangely connected reasoning functions. For example, of course, I need to know that this bird object is actually an animal. Okay, I need to know that. But at some point, I also need to know more complex stuff. So what animal is in this photo? So I need to know that the question is about existence, right? I could, let me check you for up here, another one. So what do we have here? We have keyboard, plant, table, building, etc., etc. Oh. Here you have the different objects. See, when I go over this, you see the objects which have been detected. Remember, this is the Oracle model here. So the Oracle model means the input has been annotated by people. Okay, up. So is the mouse on the right? Okay, on the right of what? Well, that's not a good question. Let me ask this one. Okay, is the mouse to the left or to the right of the laptop in the center of the picture? Now here, better. Is the mouse to the right of the laptop? Let's ask this question. This performs now a new forward pass on the model. And what you see here, you see the different heads here, and the colors of this head corresponds on the amount of, let's say, peakiness of my attention distribution. So what does this mean? Here you see the color code. Red means a large number of items is necessary to reach 90%, 99% of my attention energy, or 80%. Sorry, 80%. Blue means only a small number of items is necessary to reach a high number of attention distribution. This means that the attention is peaky. It's like closer to the rack. Here it means closer to uniform, right? So this means that the blue ones are probably ones the ones which work more thoroughly on this sample. And this is not necessarily general. It means that for some sample, for some questions, some heads do more work, for others they don't. Why? Because these heads very often learn reasoning functions. What does this mean? So for example, this head here, what does it do? Apparently, it associates the laptop here with most of the objects. Well, that's not really meaningful. Apart from the laptop, it's just kind of an inverse distribution, right? It removes the laptop from the input list. Okay, why not? What do we have here? Same thing. What I can do is I can click here, I can check this. What do I see on this side here? I can see over the full data set, what are the kind of questions which receive high peaky attention from this head here, right? Remember, I chose one of these heads here. Each head has its own attention strategy. And this head here apparently receives high energy for all questions where select reasoning is necessary, right? So with this model here, with this kind of visualization, I can find out what kind of reasoning is done by my model. And we also found out that, for example, in the Oracle model, there are many heads which provide an average uniform distribution when you average them over all the inputs, but they become very peaky for certain questions. So there is a certain specialization between these heads here to the reasoning function in language. I can detail this here, but details are in our CVPR paper. We also performed tests on experts. For example, what we did is we provided 6 different inputs here. We provided them to experts, and we asked these experts. The experts were trained for 1 hour on this model and how this model worked. They found out how this model actually reasons. And then we asked them, okay, this is the input image, this is the input question. We masked the output here, and we asked them 2 questions. What will be the output of the model? And second, does the model reason or does it perform bias exploitation? And we showed that our experts with this model could, to 75%, detect whether the model reasons correctly or not. Reasons correctly here is, of course, not necessary. We don't know whether the model reasons, right? It's impossible to find out. But according to our own estimate, a model reasons correctly if it provides a correct answer on an out-of-distribution sample. So if the answer is correct, but pretty rare, and it uses bias exploitation if it's a wrong answer, which is very frequent. So I'll go back to my, how can I do that? I'll need to stop screen sharing. Here it is. I go back to the model, to my slides. Partager. Écran. Oh. I think I should be good.
Ça doit pas être le bon écran.
Ah, c'était l'autre qui était partagé?
Là, ça me répond. Donc, je vais vous...
Thank you.
Parce que ça donne ça.
Ça devrait être bougé tout seul si on ne bouge pas la souris. Okay, thank you very much. So, what we, in order for this to work, I need to, yes, here it is. So, what we showed is that when we can learn a model from ground truth, oops, sorry, I'll just need to get pointer again. So if we learn a model on ground truth data, so humanly annotated humanly annotated data. And when we fine tune it on noisy data by going also through the BERT losses, which are necessary, we showed that this works. But we also showed that there are lots of things which get lost, because actually when the model goes from ground truth data to noisy data, there are two types of domain shifts. There is appearance shift in the sense that visual objects in the ground truth data, visual objects don't have features. You have a hot one encoded class. So we manually say, this is an apple, this is a bicycle, etc. So going from this to noisy data is an appearance shift, but there is also a presence shift in the sense that the object detector does not correctly detect all objects. So some objects might be missing. If we're lucky, these objects are not necessarily to answer the questions, but if we're not, they are. And also sometimes they're multiply detected. So basically adapting this reasoning function here. So when the data is very clean, it learns reasoning, and it's very, I wouldn't say easy, but it's very logical reasoning. There are logical steps which need to be taken and computed by the transformer to the reasoning. Going to noisy data, there need to be a couple of, I wouldn't say shortcuts, but the model needs to learn that if the apple is multiply detected, well, that's not a big deal. We need to live with that, right? And this adaptation here, it's complicated. So lots of reasoning power is lost. And so we have one last contribution, which we submitted recently, which is supervising ground truth reasoning programs. What does this mean? Well, for certain data, we have ground truth on reasoning, right? So when you take input data like this here, right? We have two forms of data sets. The first data set is the one where people, so humans, got the image and they provided their own question and their own answer. So we can't do anything on this data because the way how this question needs to be answered is in the head of the annotators, and we can't open their head. The second kind of data set is different. Images have been presented to human annotators, and the human annotators did not annotate the question. They annotated the objects in the image and the relationship, for example, geometrical, spatial, logical relationships, and then a procedure, so a computer science program, correctly or manually, automatically generated lots of questions for each image. And on this data set, we can do things. Because we have ground truth reasoning programs, if the question has been automatically generated, we can generate in a specific form the reasoning program. For example, on this image here, and the question is, does the boat to the left of the flag look small or large? Well, the same program which can calculate the question can calculate the program, which is you first need to select this flag here, then have a relationship operator which gets me the object right beside to it, and then a choose size operator which checks the size of this object, right? So this thing here, this is a reasoning program, and this is nothing else than a mathematical expression, which is a tree. It can be encoded in a tree, as can any regular expression or any Backus-Naur form, basically, any context-free grammar. And so that's exactly what we did. So what we did is we took the language, the vision language encoder we had before, right? So we have the tokenizer, we have the object detector, we have a language-only encoder, vision-only encoder, we have this cross-modality modules, and we have the VQA head, which predicts the answer, and we have a program decoder. And this program decoder here basically decodes the program. It predicts the program. And then we have a loss in here, which says, yes, this is the correct program. So basically, we take the head of the network and say, please reason this way. You can't supervise more. We say, please do this. This is the exact kind of logical thing you need to do. Okay, that sounds kind of strict, okay? And what we actually also do is we do this in initial stage. Once this error here, this loss converges, we open it, we remove it, and we fine tune on VQA, because sometimes this is a little bit too strict. But what it helps is we inject this into our transfer scheme. So we learn first, we train on the oracle, on the human annotation, So this model learns perfect human logical reasoning. Then we also add this program prediction head. So the model not only learns how to reason, not to reason, but also how to reason. And then we switch over to the noisy data. We maintain the link to program supervision. And this maintaining the strong links with program supervision helps the model to attack this appearance shift and presence shift here. And we see that we lose lots of less information. We have a huge gain so here, for example, you see the baseline. This is when we transfer using the Oracle, and if we supervise, we get higher performance here. A little bit of intuition into this program supervision, because we also approach this from a theoretical point of view. So basically, we provided backbounds that show that this program supervision also, and this auxiliary loss, because it is an auxiliary loss, it also decreases sample complexity. And I'll just give an intuitive explanation how this works. The real proof is a little bit longer, but basically, when you do a visual question answering, you have this vision and these questions here. This goes into a model. Let's just see a classical model, and you output here your answer, right? So Y is your answer class. This should be a theta here, same as here. So your model here learns what? Your model consists of what? So these are consecutive layers here, yeah, right? So either an MLP or a transformer with consecutive layers. And there are two things. There are blue things and green things. The blue things are basically, this is knowledge about the mathematical or logical reasoning function. If I supervise here with the correct answer, there is no reason why any knowledge about the reasoning function should go into these layers here. All the knowledge about reasoning will be put into your parameters, network parameters, and this function here, this neural network will learn how to reason given a question and an image. The green stuff here is the intermediate activations of my neural network, and this will only contain the minimum amount of information which is passed between layers, such that the layers know what to do, right? But the layers will take this information, and the amount of reasoning or the reasoning they will apply will depend only on the parameters. So this means that the reasoning function, so reasoning function means the mathematical function which takes a complex visual image, the encoding of the question, which needs to deform the image to find out what is the answer. This full thing here needs to be learned just by supervision here, and the decomposition here is not supervised. Now, if we also inject here a second head which predicts the program, what happens here is that part of the parameters here, well, before the parameters encoded knowledge about the mathematical function, well, part of the knowledge goes now into this representation. This is necessary because we supervise program prediction. So if we supervise program prediction and this loss is low, then parts of the reasoning knowledge goes in here. So the blue stuff slides into the hidden layer, right? Now this means that as information goes through the network, more and more reasoning knowledge needs to be here. But this also means that since we have information about the reasoning function here, that this knowledge here can be, this full function here can actually be decomposed. So as the layers are later and later, as we pass through the network, the layers actually, since they have this blue information here, they need to learn only a couple of reasoning modes. So for example, we can decompose the full reasoning function into functions per question type. The whole thing here can be actually formalized. It can be put into mathematics, and then we can prove this. I'll stop here. As an intermediate conclusion of what I wanted to show in this lecture is the deep toolbox, which is totally not exhaustive, but the most important tools we use are MLPs, convolutional neural networks, RNNs, graphs, and transformers. Transformers getting all the attention, sorry, play on words, they get all the attention recently, and they're even now applied to images. Now, this is something we need to reflect a little bit on, because I told you that MLPs are not the best choice for images because we learn the same things all over again, right? They are not shift invariant, and we learn the same reasoning functions for each position. Now, it's not as hard as transformers, but transformers is the same thing, right? Because transformers, when you apply transformers on images, that means each pixel can attend to each other pixel. There is no inductive bias anymore to learn that at the first layers we attend to closed pixels, then we integrate to large, etc., etc. All this goes away. We don't use this anymore. Well, it turns out that for most reasonable data set sizes, CNNs completely outperform MLPs and transformers. But once you apply your reasoning, your model on Google-style data sets, and I don't talk about ImageNet. ImageNet is only 1 million images. I mean like hundreds of millions of images. So the kind of data which only Google can use, then actually this model, transformers, is much more general than CNNs. So transformers can represent CNNs and much more. They are higher complexity class, and they largely outperform CNNs. And lately, the latest papers go even into the direction of MLPs. So that's unfortunate. All this deep learning science we did over the last years apparently seems to converge towards MLPs. If you are Google, if you're not Google, then everything I said still applies. Second conclusion is what is missing in this lecture. Well, obviously, I only covered these inductive biases for images. I didn't go into details. I only really slightly covered supervised learning and self-supervised learning, but there's lots to do about reinforcement learning. I think Marc and Amaury talked about domain adaptation, so at least that's covered. I didn't have time to go a little bit into machine learning and physics. I apologize for this. I know that this is really important here, but I didn't have time to talk about this. And obviously, I did not talk about theoretical models. There was lots of really exciting theory currently done in deep learning because we found out that these classical models and bounds were not applicable to deep learning. And people are working on new bounds, but this is really not my area. So I think you had lectures on this by Marc and Amaury. I'll switch over now back to my computer and not yet. Let's go to the practical part, because the question is how do we code all this? What is that? Can I close that? Oh, here it is. So the second part of the lecture, so what I will do is I will talk a little bit about deep learning frameworks and tensors. I will talk a little bit about automatic differentiation. Oh, sorry, I'll need to get my laser pointer again. Talk a little bit about automatic differentiation. I'll give you an example how to implement an MLP for MNIST. And what we'll do is we'll take this example and derive a convolutional neural network from the MLP. And we can do this together, and I'd appreciate your help on this. I will ask you questions and you can tell me how to do that, okay? So first of all, in deep learning, we manipulate tensors. So this is a well-known figure by Anima Anand-Kunar, scientist at NVIDIA. So what are tensors? I mean, in physics, if you're physicists here, forget the word tensors, because in physics, they mean something else. In deep learning, machine learning, tensors are just generalization of matrices with additional dimensions. They don't have the physical meaning of tensors. So a scalar is a tensor, a vector, a matrix. Then we have tensors of order 3, 4, 5, etc. And images can be, for example, 2D tensors. Then videos can either be sequences of 2D tensors, or they can be a 3-dimensional block, for example. Even a single image can be 3D data if it has color. So each channel, for example, here is one additional dimension. So we learn, we will do machine learning on lots of different tensors of forms and sizes, shapes, etc. So a couple of examples: tensors of dimension 2. Well, the first dimension is always the batch dimension. We didn't talk about this at all, but it's important. I will introduce it now. When we do machine learning, when we do deep learning, we never work on a single sample. So instead of taking a single input sample and doing the forward pass and calculating the gradient, what we do is we take multiple, it's called a batch, mini batch or batch. We take multiple samples, we calculate the forward passes of all of them in parallel on GPUs. Mostly we calculate gradients, we accumulate the gradients, for example, through sums or means. And when we do a step of gradient descent for one batch. What does this do? Why? Well, there are engineering reasons because it can heavily parallelize, but there are also actually optimization reasons. So it kind of smoothes the gradient, right? Calculating the gradient on the full data set is not possible mostly. It's also not desirable because then your gradient is too smooth and you're really blocked very often in a small minimum. So lots of regularization properties come from the stochastic nature of gradient descent. So the fact that we calculate it on a couple of samples only on a batch, and which creates a little bit more smooth than on a single image, but sufficiently noisy. And this noise is actually responsible for lots of the regularization properties in deep networks. And this is also recently shown in theory. So the first dimension in our tensors is always the batch dimension, right? The second is some kind of signal dimension. So if you have like a 1D signal, well, you also have already a 2D tensor, right? So in your lines, you have the different samples, and in each line one sample, and different lines are different samples. Another example would be the output tensor here, right here. The output, well, one is the prediction of different classes, and one is the batch dimension. What could be a tensor of size 3? Well, for example, the intermediate activations here, right? What do we have? We could have a batch dimension is always there, signal dimension if it's a signal, and feature dimension. So each unit here is one dimension. If you have this for different time steps, it's another dimension. If you have batches, it's another dimension. We already have 3. So we go up to 5. 5 is pretty common. 6 starts to get not so frequent, but 5 is pretty common. What is 5, for example? We could have the batch dimension here. Then if we do video processing, then we could have the spatial X and the spatial Y dimension of an image. We could have color channel for actual RGB, red, green, blue, and one time dimension. So the data itself is already 4D. Well, the data is 3D plus color, so 4D plus the batches. So this means that you will also very frequently load 5-dimensional tensors in your computer. And how do we do this? Well, what we need to implement are functional mappings. So we have inputs, they are tensors. Then we have this function here, which are code. This is program code, but they are code which is parameterized by theta. Our parameters, they are tensors. They create intermediate activations and final activation. That's again a tensor. We calculate the loss function. That's again a tensor. And it's calculated from the ground truth, which is also a tensor. So the whole thing is basically computer science code in tensors. Now, there are 2 different strategies. We can learn all this. Okay, I'll try to be as simple as possible. We can do it symbolically or imperatively, but symbolically is kind of overloaded as a term. So what does this mean? You can either define this graph here once. So you define, this is a graph, right? So calculation graph, so calculations and values go in, and each edge here is compute. And you can define this graph here symbolically. That's what the first generation of TensorFlow does. So your Python objects are symbolic graph instances. And whenever you want to do something with this graph, we'll give this graph to the inference engine, and you tell the inference engine what it does. That's one thing. TensorFlow up to version 1 did that, and it was painful. That's my personal opinion, but it's painful. The second possibility is what, for example, PyTorch does. It says, okay, we don't want to do symbolic programming. We want to do what is called imperative programming. Imperative is a big word, but just means do programming as you do it in C, C++, Pascal, whatever. So you execute one instruction after the other. And execution means you change the state of your machine. It's like a Turing machine. There is no symbolic calculation graph calculated in advance, right? This is what we do. This is what computer science people mostly do, unless they are AI guys. So what we would like to do is we'd like to do this kind of thing in an imperative language like Pascal, C, or Python. And that's what PyTorch does. So these are two competing frameworks. PyTorch is so much easier. There's a little bit of personal conviction in there, as you can see, but that's okay, I think. So PyTorch is so much easier that in version 2, TensorFlow changed its strategy, and they have now a PyTorch mode, which they call obviously Eager mode and not PyTorch mode. So both are working the same way, and my team and most academic teams I know use PyTorch. So let me just show you how this works. So do you guys know a little bit MATLAB, perhaps? Anybody familiar? So if there are lots of physicists and image processing guys, I guess you're pretty familiar with MATLAB. So PyTorch is a little bit like NumPy plus Python. NumPy is like MATLAB for Python, and PyTorch is automatic differentiation for Python. So what does this mean? First of all, we can create tensors. I'm sorry, I will switch back because now it's time to use my computer. In my own, I will use terminal. So, okay. I'll go back, share my screen. Okay, how can I remove this guy here? Okay. So I'll try to make the text a little bit bigger. For some reason, it doesn't want to. Okay. Can you read this? I don't see the chat. Oh yeah, I see the chat. Okay. I hope you can read. If you can't, tell me. Okay. I have a little bit trouble increasing the font size. Normally I can do that by just, for some reason, this doesn't work with the shortcut, but perhaps I can do it with where's the font size here? Text here. Wow, this will be big. And it didn't change anything. Okay, sorry. So what I will do is, first of all, I will just activate my Python environment. So I have all my Python stuff in a virtual environment. So I run Python. And I will import Torch. So Torch, that's PyTorch actually. Torch is the library. It's sold as a deep learning library, but it's not really a deep learning library more than it's a tensor computation library, which features a package called Auto-grad, and which performs automatic differentiation, so automatic gradient calculation. And that's a little piece of magic, which I really love. But let's first start with just pure tensor processing. So for example, we can calculate, take some tensor here, for example, another one. I can also, let's take a random tensor. So this is random tensor. That's really MATLAB style. So I can, for example, also take a second one, random tensor. That's the second one. I can say, for example, A plus B is the matrix multiplication of both of them. And this goes even up to slicing. I can do, for example, say, so this is one element of my tensor. This is a slice. So that's the first, not a second line. Yes, they took the good things of MATLAB and the good things of C Unlike MATLAB, indices start with 0. So the first element is actually 0, 0, like in C, right? Not 1, 1, like in MATLAB. But apart from that, you can basically slice horizontally, vertically, etc., etc., etc. You can reshape your tensors. You can say a dot view 1, 9 gives me a single vector or a single column vector. It's like reshape in MATLAB. You can even do nice stuff like, for example, you say, so this is my A, all my A's which are smaller than 0.5. This gives me a logical matrix. I can use this as an index in my A and tell me all these guys will be 1, like in MATLAB, same syntax. I just thresholded my matrix, well, one-sided threshold. So yeah, this is basically much like MATLAB. So I'll go back to my slides, but this time I use them on my computer, so I don't need to change back and forth. So what we'll do is, yeah, first of all, automatic differentiation. So what we need to do is, so I'll pass from frameworks and tensors to automatic differentiation. What does that mean? Well, this means we still want to do a gradient descent, right? So we have this model here. H is my model, so h of x and theta are my parameters. So what I want is I want to do a forward pass of this model, calculate the loss function with respect to the optimal values, the annotations, and I want to take this function here, and that's really a function. It's not a value, it's a function. And I would like to derive this function with respect to what? Well, to anything. Well, mostly for training, I would like to derive it with respect to parameters, because then I can calculate this gradient vector here, and I can do gradient descent. But the nice thing with of PyTorch and TensorFlow and these kind of things is that automatic differentiation can be done with respect to anything. So basically, you take a function, a numerical function, and you can derive any tensor with respect to any other tensor. And it's exact differentiation. Obviously, it's numerical in the sense that you get a numerical value out of it, but the numerical value is not numerically estimated. It's exact calculation using the chain rule. So how is this done? So for example, let's take one example. A very simple function could be a linear layer of a neural network. So X is my input. This is my numerical input. This is my, for the moment, current parameter, right? And my output is just a dot product. So Y is my dot product between W and X. And what I would like to do is, for example, well, calculate the gradients with respect to X and with respect to Y, to W. Obviously, if I want to train my model, what I need to do is add these gradients here, right? But sometimes I would like to perform these gradients. For example, if you do adversarial calculations, I will not go into detail what this is, but for those of you who know what adversarial examples are, well, for these very often you need this kind of gradients here. So you can use both, and Auto-grad is actually completely agnostic to all of this. It derives whatever you want. So going back to my model here, what I will do is I'll just, oh no, that's not possible, obviously. What I will do is I'll just create I'll take the same numerical example here, I'll just recreate it. So what we need is, do I still have it? Don't want to retype it, something like this. We said 5.3, right? So X is 5.3. Good, for some reason, what I also want is, I would like my type to be a float. Okay, let's not work with integers, but with float is just much better. So I have now a float tensor, and I'll take a second one. So this is now my W. My W will be 7 and 1. That's my example. So now I have these two tensors, right? What I want to do is I will create my output tensor, and that's torch.dot product. So the dot product of W and X, and Y has a value. So now here I really want to focus your attention to the fact that this is an imperative language, right? And once more, imperative language means that at each step you perform a calculation and you immediately have the output, right? So in the early version of TensorFlow, when you wrote something like y equals torch dot dot or something like that in TensorFlow, it means that you create a symbolic Python object which performs calculation when you pass it through an inference engine. This is not what happens here. So this line, once executed, performs the numerical calculation and provides you with the output, like C, C++, Python, NumPy would do, right? So this means that this is really important, because this means that you can really easily debug your model. You can at each time print whatever output you want. Print y gives you the output, as I just said. So this is really, really important. It's debuggable. Now, what I want is, I would like to derive this thing, right? I would like to derive the derivative of y with respect to w. Now, in PyTorch, if you want to derive, you say backwards. Why backwards? Because for some reason, I don't have time for this today, but deriving means you first go to a forward path through your neural network and then your backward path from your result backwards to input to calculate the gradients. This is basically just a numerical calculation of chain rule. So chain rule in calculus tells you how to calculate gradients of composite functions. And if you apply chain rule to all networks, this is just exact calculation. Once more, when I say we calculate gradients numerically, it's not a numerical approximation, right? It's not finite differences. It's really the exact chain rule evaluated on exact numerical values. It does not approximate the gradient. So for this reason, in PyTorch, we say something like y dot backwards. Don't try this at home because it will fail. I didn't do something I should have done, and that was on purpose, but let's just say I would like to do that, right? So y is the value with respect to which I would like to differentiate. I don't give the value to on the denominator here because it derives with respect to everything. The problem is it will not work. So what happens here? Does not require grad and does not have grad function. Now, what I just asked here does not make any sense. It does not make any sense, right? Why doesn't it make any sense? Because it's a consequence of the imperative nature of Python. Once more, we defined x, we defined w, these were numerical values. We created the result of the dot product. This is a numerical value, and you cannot derive a numerical value. The derivative of 38 does not make any sense, right? Why would we derive 38? And that's all we have. We only have 38 because Python is an imperative language. So this clearly doesn't work. But what can we do? Obviously, we will be able to do it because else I wouldn't be sitting here. So what we can do is, we don't want to derive y, the numerical value, we want to derive the function which calculated the numerical value. And what PyTorch does, if you ask it, if you're really nice to it and you ask it, it keeps the calculation graph of everything it calculates. But we didn't do that, so I will do it now. Let's create the same tensors as before. So x is a tensor. I'll just add one more flag here, which is called requires grad equals true. So what did I do now? I informed PyTorch that I would like to create a numerical tensor in float precision, and it requires gradients. So whenever any calculation is done using this tensor, PyTorch will keep all traces. It will keep traces to the numerical function, no, to the computer science function. I will try to avoid the term numerical, to not make the impression that it's an approximation, right? So it will keep traces to the exact compute code which created the value. I'll do the same for W. W was this tensor here, same. I say requires grad equals true, okay? So if I now check what x and y are, they are the same numerical objects, they still have values. I still have the numerical values, but also I have this requires grad thing. I now perform my same computation, y equals torch dot dot, so I calculate the dot product. It still gives me the same numerical value, but this tensor here has a couple of fields, and one of it is grad function. So grad function here is nothing else than a pointer, a reference to Python code. And which Python code? Well, the Python code which calculated y, right? So we have, and which is obviously which one? Well, it's the dot product. So this in reality is a pointer to the dot product function, and not only the function, but also its arguments, right? So this whole thing here includes the pointer to the code of the dot function itself. By the way, also its derivative, and also to the arguments here. Now, when I say backward here, perfect, will be done. So it calculated the derivative. Now, where are they? It calculated the derivative of y with respect to all tensors for which I have declared requires grad equals true. So when I ask for the value of x, I'll get its value. When I say x.grad, well, this is the gradient, well, the partial derivatives of y with respect to the two values of x, and which is, oh, I inversed, sorry, with respect to the slides. It's not a big deal. But anyway, in this example here, obviously this is a dot product. The gradient of x is w and the gradient of w is x. Same for y and y dot grad. I have my tensors. Okay. Is this clear? I will take questions here if anybody has questions on this part. Okay, sounds good. Now there is one thing you need to be aware of. Obviously, if you have a very large neural network, so let me just go back to my slides with the transformers or something like that. So let's just think, take this Helix-Merth model here. So let's just imagine this thing here. So this is an image, this is a question, you have lots of things, and every self-attention layer here is multiple heads, lots of projections. All these are lots of different tensors, matrices, calculations, etc. So once you do this forward pass, you apply your gradients here, your backwards pass. It goes all the way back, but you need to imagine that all these forward passes here will calculate a calculation graph, right? So every time you perform computations here, you will keep the intermediate activations, you will keep links to intermediate computing functions, and all this uses up lots of memory, and mostly GPU memory if you're performing on GPU. So this comes with a price, but it's the obvious price, right? It's a price we pay really happily. The price is that whenever you require gradients, you keep the compute history and you have a calculation graph. So going back to the differentiation between at least the original TensorFlow library and PyTorch is the computation graph in TensorFlow, at least the original version, is calculated by hand. So the user calculates and designs a computation graph, right? By hand, and then launches an algorithm which differentiates it. PyTorch uses automatic differentiation. So basically, code is executed in the background, calculation graphs are stored and maintained, and then the library backpropagates through it. The nice thing of this is you can backpropagate over loops, over if statements. You can do, and now there should be an outcry. Students should be shocked, right? You could do something like if equals higher than, I can't do it right now because I'm in Python now, but I can do something, or I could do it, even in Python, it's obviously possible. I could do something like if x is higher than 6, then y equals 3, else or else, just else y equals 4, right? Done. Oh. Boolean will of tensor obviously didn't respect stuff, but anyway, it should work. And then I can do y.backpropagation, right? So I can backpropagate through this if statement. I can backpropagate through loops, through object instantiation, through object-oriented code. Basically, PyTorch and automatic differentiation is the dream. I'm a little bit fan, you can see that. It's the dream combination of numerical analysis and high performance and high value computer science programming. You can backpropagate through exception handling and whatever you want. You can backpropagate through everything. And now is the shocking part. Why is nobody shocked? Why wouldn't anybody object through this? What's the problem here? I mean, there isn't a real problem, but there should be one. Nobody's shocked by this? Nobody's listening, right? Are you guys still here? Yes, that's the problem here. I forgot that x is not a scalar. So I should have wrote this by x bracket 0. So no, that's not the problem. This is all just my own stupidity. If I write this code as x bracket 0, for example, then x is a scalar. No, that's not the problem. Exactly, that's the point. What is the function not differentiable? Well, that's the point, actually. And the thresholding function is obviously not differentiable, right? But lots of things are not differentiable. Max pooling is not differentiable. So the real answer is just we don't care. So what is done is we differentiate through the function, and the approximation is basically when the function is not differentiable. Then we backpropagate and ignore the non-differentiable part. So in thresholding, for example, if you do thresholding, if you're far from the threshold, then there is no problem. If you're right at the threshold, the derivative on the threshold is not defined, and you backpropagate and you ignore this. You just keep it constant, right? It's the same thing which is done by max pooling. So the real answer is you should be aware of it. Mostly is be aware of it. It doesn't change so much, right? ReLU activation functions are not differentiable. They work so much better than sigmoids, which are differentiable. So yeah, the real answer is we really don't care. We should, we don't. So, but you should be aware of it. Okay, so I'll go back to my slides. To the other ones. And what I will show you now how this is done with a real neural network. So basically what you could do is you could implement a real neural network just by using all this. So you define your X's and W's and you use your network as a sequence of all this code. You calculate your gradients yourself. You can even implement your gradient descent algorithm, stochastic gradient descent yourself, and this can be done. And sometimes is done if you really want to handle and everything. If you want to do everything manually, sometimes it's necessary, but mostly it's not done because on top of Auto-grad, there is this additional library module.neural network, which can do lots of things. Yeah, something I forgot. I just briefly go back. Sometimes when you have your Y, oh, I forgot it. No, yeah. You can detach your gradient history. I didn't put the example here, but for example, sometimes you want to just take a tensor, just take its output value, and you want to detach the full history of the recent, basically the calculation graph. You can run the detach function. Else you couldn't, for example, take all the output values and put them into a matrix and do other stuff on it. Okay, that's a detail. So let's go back to what I wanted to say. You have this library, it's called Torch NN modules, so neural network modules, where basically once you do this, all this optimization issues, gradient descents, etc., they're handled for you automatically. So how you do that? You just need to subclass this function as this module, this class basically a neural network. But it's obviously object-oriented, so this is done by computer scientists. But computer scientists with a strong background in numerical analysis and deep learning, obviously. And so you just redefine your forward pass and obviously your constructor, your init function. And the forward pass basically takes your data, and here you put all your code, which calculates, for example, a forward pass in a neural network. So for example, what does this thing here do? FC1, FC2 are two fully connected layers. What are fully connected layers? They're basically just matrices with which you multiply your data. And here you prepare the fully connected layer. So torch.nn linear, for example, what is this? Linear is not a function. Linear produces a functional. So linear, you give it two values, the number of input values, the number of output values, and it produces FC1, a function, and this function here takes an input and applies a parameter, okay? So this means that this thing here, this linear function also, it not only creates the functional, it also allocates the parameters, it declares the parameters with the optimizer. So when you run later an optimizer, it knows that this thing has parameters, needs to be optimized. And there are lots of behind the scene things going on, which at the beginning can be a little bit confusing, but which are really powerful. So once I set up my two functionals, my forward pass is basically just take my input here, reshape it a little bit, apply one linear layer, apply one ReLU. I didn't explain what this is, but this is just a pointwise nonlinearity, apply a second linear function and return this. Okay, so this is my neural network. How can I use this? My neural network is called MLP here. I first instantiated a new instance of my MLP. I suppose I have data here, so I didn't put the data loading on this slide here, so I just throw data at it, gives me an output. I calculate the cross entropy function and I perform the backward pass. That's it. My backward pass goes through the cross entropy function, through my model, finds the forward pass, and differentiates with respect to all of this. Okay. I give an example. Let's talk on MNIST. So most of you guys perhaps know the MNIST example. So MNIST is a data set which was introduced a couple of years ago, well, 22 years ago by Jan LeCount. There are small input images, 28 by 28 pixels. There are 60,000 training images and 10,000 test images. There is on his website even some kind of leaderboard where you tell you which kind of network obtains what validation performance, and the latest performance is so big that it's not actually validated in percent, but in number of samples which are wrongly classified. So the dataset is basically very saturated. The dataset is so well known that PyTorch even has its own data loader. So you just in PyTorch just write datasets.mnist, and when you say download equal true, it even downloads the dataset itself from Jan LeCount's own website. So it's really pretty well known. So you can set up your data loader. I will not go into details, but basically this thing, you can also provide it with a couple of transformations. Here you can put functionals which normalize the data. So this ensures that the mean is 0, the standard deviation is 1. So it centers the data. And then what we want to do is we want to do mini batch, right? So this is our network. We'll define it later on. And we would like to calculate the loss function. We would like to calculate this gradient here. And we would like to calculate this gradient on batches. We would like to define a batch size of, let's say, 32, 64, 5,000, and calculate these batches automatically. And basically PyTorch does that. So whenever you have your own dataset object, you can write your own dataset. Writing dataset classes is really easy. And with my students at INSA, we actually rewrite the dataset class for MNIST. We use our own. Can be done in 10 minutes. So once you have a dataset class, which basically just defines how you access to a single sample in your data, can be done really easy. If your dataset is an array, then it's even almost trivial. And then there is this data loader class in PyTorch. Once you give it a dataset class, which you mostly do your own, and a batch size, and some information on whether you shuffle, what it does, it automatically batches your data. It shuffles it at each epoch, at each path through the data, it randomly shuffles it again, and it batches it. It provides you with batches. The first dimension is tensors. They're nothing else as tensors, where the first dimension is the batch. And it makes deep learning really easy. Obviously, a couple of restrictions. If you have variable length data, it's a little bit more tricky. Then there are tensor dimension conventions. So as I said, the first dimension in a tensor is always the batch dimension. And when you calculate losses, for example, you mostly reduce these losses over the first dimension. So the gradient is mostly averaged over the batch dimension. So that's a typical thing. But you can handle that. So you can change that if you want. Can somebody just tell me on the chat how much time I have, because I forgot when I need to stop. Then the second dimension is the channel dimension. Channels are important if you use images, for example. If you don't have images, channels, thank you. So it's 5:45, good. That's lots of time. It's very, okay. I will not explain channels a lot. I will come back to it later when we'll talk about CNNs. And then the rest of the dimensions, well, they depend on how you deal with them. You can deal with them in your own way. So for example, rows and columns and images. So let's talk about, I give you a very simple model for MNIST. So we take again a subclass of the Torch neural network module. We call it logistic regression. And logistic regression that's a funny name because actually logistic regression comes not from the machine learning community, it comes from statistics. And this model in statistics is actually mathematically equivalent to a neural network with a single linear layer followed by a sigmoid or softmax attention nonlinearity. So we also call this logistic regression here. So my data here will be my images. And what I will do is I will allocate a single linear layer because it's logistic regression. And this linear layer goes from 28 by 28 pixels to 10 output units. So can anybody tell me why, I'll check if you're listening, why do I have 10 output units here? So I have one input layer, one hidden layer. Now there's no hidden layer. And on 10 output units. Why do I have 10 output units here and not 12 or 15 or 30,000 or 1? 10 digits, exactly. So we want to do classifications. We have 10 digits from 0 to 9. So we directly map from pixels to digits. So one thing is my input tensor comes in as a 3D tensor. 3D because I have batch size, right? Batches, always batches. And then my X and my Y, my Y and my X's. So this is 28 rows and 28 columns. So the first thing I will do is I will reshape my input images into single vectors. So each sample is a single vector. So I reshape into a 2D tensor from 3D to 2D. Why 2D? Because I keep my batch dimension here. And so here what I provide is the number of elements in these dimensions. And this would be here, how many? Well, as many as my batch size, right? I don't know my batch size because I keep it agnostic to batch size. What saves me here is when I do reshape, as in MATLAB, for a single dimension, I can ignore the number of elements here and just say -1 because there is 1 degree of freedom here. So if my batch size is 50, then this will be 50 here. So I reshape it to 50 times, well, the amount of elements in my vector, which is 28 by 28, right? So this does not change. This does not change the data, and it's also zero cost. Zero cost apart from the function call itself, right? And the updates of the metadata, because the data is not rearranged. It's just the metadata of the dimensions updated. So zero cost. And then I apply my matrix here. And this matrix will be what? Yeah, let's do a little bit of exercise. what is the size of my matrix here? So this is a linear operation. This is a matrix multiplication. What's the size of my matrix? Basically depends if I do a calculation from the left side or from the right side. Let's imagine it's on the left side. Let's say it's W 10, yeah. But this, excellent. Yes, exactly. So it's 28 by 28 times 10 because I multiply my input tensor, no, my input vector, and my output is size 10. And this is also the reason here why my linear layer is 28 by 28. So this is a multiplication here, obviously. So this is a numerical value. I'm too lazy, I don't want to calculate this, but obviously this is a couple of values. And what did I want to say? Yes. So the output here is a vector of 10. Good. Something else I'm missing here. How many parameters does my model have? I'm getting a little bit. You're too good, right? You're all deep learning specialists. So I'm trying to be a little bit mean. How many parameters does my model have? No need for the numerical expression. Just give me the calculations. Okay, nobody. Well, how many parameters does it have? Well, at least the entries of the matrix, so 28 by 28 by 10. These are parameters, and since I did not provide an additional parameter here, this is a model with bias. Bias means there's an additional constant bias term, which is of times 10 later. Exactly, good. So we have 28 times 28 times 10 plus 10 parameters. And PyTorch basically has a function which gives you the number of parameters for any complicated model, because if you take, for example, in a transformer-based model or something, the calculation can be not as straightforward. So this is my model here. So this is a class, right? So it sets up my model. So you can imagine that if I do a transformer-based model, I have a couple of hundred of lines in here, can be quite complicated. So what I do in my main routine, well, first I set up my model. So logistic regression here, that's obviously the number. So this instantiates my class. So this instantiates my loss function. We will use the cross entropy loss, which is the standard loss for classification. So this will create a functional. So cross entropy is a functional. Okay, it's a function. This sets up my optimizer. So I choose my optimizer. I can choose SGD, Adam, whatever optimizer I like, depending on my religion. And what I tell it is here, and that's really, really neat. That's really, really neat. I give it my model.parameters. So my model is this logistic regression here. And dot parameters, how does it know the dot parameters? Because I used standard deep learning layers. This linear function here sets aside a couple of parameters, well, this matrix here, and adds it to the parameters dictionary, right? So model.parameters knows which parameters are in there because the standard routines here know about it. If you want to do your own layer, well, then you need to add the parameters manually to the model and also their meaning and how they're updated, right? And that's my learning rate here. That's a couple of intermediate statistics for myself. And then basically what I do is I just do iterative training. So one for loop, which tells me how often I go through my data. So each epoch is once I go through my data. One for loop here, which goes through my batches. So this is my train loader. My train loader will give me at each call here a batch index and then data and labels. So the train loader gives me the data and the labels. Data here will be a tensor of three dimensions, right? Batch dimension, X and Y dimension, right? The reshape is done internally, remember? So the batching here gives me a three-dimensional batch, and the labels, so this will be a 2D tensor. Why is it 2D tensor? 2D because one is the batch dimension, and the second dimension is the label dimension because it's hot one encoded. So whenever I do gradient calculations, the gradients are accumulated. So I first call zero grad, which means all gradients set to 0. So this is my forward pass. Model here, remember, model is my instantiate model here, right? I'll take this data here, which I got from the train loader, I pass it through the model, I get my predictions. These are my predictions. I calculate the loss between my predictions and my labels which I got from my train loader here. This is my loss. My loss is a scalar because basically my cross entropy loss, since I didn't say anything here, my cross entropy loss by default just reduces over the batch dimension to a single scalar. If I don't want that, I cannot reduce, but obviously since I want to differentiate it as scalar, I want to have a gradient, which is a vector, and not a Jacobian, which would be a matrix. I do reduction. So obviously, if I say here reduction equals false, then I get a vector and I would need to calculate the Jacobian, but that's not useful for optimization. So loss point backwards now goes backwards all this calculation trace, right? So remember, whenever I perform something here, loss here keeps, loss is a value, but it keeps a pointer to the cross entropy function and the arguments. Y keeps a pointer to the fact that we did a model, a forward pass here, so it's basically a forward pass function, blah, blah, blah. So we can backtrace here the full calculation graph. And then, so it sets up all the different gradients. In the parameter vector, we have all these .grad vectors. And so optimizer.step here will basically just do one step of gradient updates. It will take all these different parameters .grad and updates, and it takes into account the loss. I'm missing the word. My learning rate. Good, that's it. Then what you can do is you can calculate the winner class and do statistics on train error, etc. I will go quickly with this. If I run this, and I actually will run this. Oh, what's happening here? Hold on, too fast. So if I open now, this is the same code as before. I have a train data set. I also have the validation data set, but for the moment it's not used. And we have now, oh, that's the solution. No, don't look at the solution. Where is baseline? So here we have the model as on the slides, logistic regression. We have instantiated model, cross entropy. We have cycling through. And the only thing is for each 100th batch, so each time my batch index modulo 100 is 0, I calculate the draining error. So if I just run this on my computer without GPU, right? Without GPU, so this is running on my CPU, and we're running in real time 1,000 batches. My batch size is how much? I forgot about that. My batch size is 50. So I already ran the second time 1,000 batches, so 50,000. So we already have 100,000 forward and backward passes, right? And that's on my CPU. My GPU will be just fly away. Also, by the way, if you want to do the same thing on GPU, PyTorch can do this immediately and very well. It's just say model dot to device or something like that, to device, and you give it the GPU device, and you can say data dot device, and everything is done on the GPU. It's completely transparent. The only reason why you really need to code your own GPU code is when you provide any mathematical function which does not yet exist in the PyTorch library, then you need to do your own CUDA GPU code, but else it's completely transparent with respect to GPUs. So we were basically done. Last part, we have a half an hour, and this is your part where you come in. So what I show you is, this is the example output after a couple of epochs. So if you do a logistic regression after 10 or so epochs, the training error will go down to 7.6%. That's not much. Also, by the way, obviously, this is not representative of the performance of the model because it's training error, right? In reality, what you want to do is you want to have a holdout set, so a set which has not been seen by the optimizer, and you want to calculate your error on this validation set. We'll not have time to do this today, so let's just work on the training error for today. And what you can do is, well, I would like you to do something like LearnNet, so use convolutions, okay? To do convolutions, well, I'll give you a little bit help, but if we do that, basically after 75 epochs, we can go down to a train error of 0.04%. And in terms of validation error, it's the same. So the validation error is much more lower. The reason is that we have 60,000 training samples, and logistic regression, just think about what logistic regression does. It takes the whole set of pixels, and let's just take like 2 or 3 minutes on this. You have a training sample here, right? Each pixel is taken, and we have a linear model. It's a generalized linear model. It's not a real linear model. It's a generalized linear model. But it has also, by the way, a linear decision function, right? Logistic regression, as a linear model, has a linear decision function classification. So it needs to be linear separable with a straight line. And more importantly, if you have it directly maps pixels, so gray values of pixels, to classes, right? So if you have this, if you take, for example, this digit here, it maps the values of this digit during training time to a class. Let's move this digit here 3 pixels to the right, right? Let's move this pixel, this image, 3 pixels to the right. Logistic regression will not have seen this example. It's a fresh example, which means that theoretically in logistic regression, you need to see all input shapes at each position in the image. If you take an input shape and it's in a different position, as if it has been never seen, right? Because it maps pixels to classes. For convolutions, this is not the case. So once you have seen a specific shape, once somewhere in the image, the model output is the same, whatever position it's in. And this is a tremendous advantage, right? It's a tremendous advantage. And this means it's even more surprising that now on this large scale data sets, MLPs, so on this Google kind of data sets, MLPs start to outperform transformers and CNNs. This really means that this information, this basically means that MLPs have this problem of being position non-invariant, so dependence position, but this also means that position encodes lots of prior knowledge, which is exploited by these models, right? Seeing a bicycle on the upper left corner gives you an advantage, a context advantage, which is really powerful. This comes with the downside of not being translation invariant. So on this small data regime, this downside of not being translation invariant is more important than this taking into account context. But in this high data regime, the downside is not so important, but this context becomes powerful, and MLPs now outperform CNNs. Okay, now going back to MNIST, we don't have this, we are not in high data regimes, so CNNs will be more powerful. So what I propose to you is, where is it? Sorry. This kind of model. So I'll give you the architecture. Let's take one convolutional layer with 5 by 5 filters and 20 output channels. One more convolution layer, so a second layer, which has also 5 by 5 filters and 50 output channels. One hidden layer with 500 units, so which takes this 50 output channels and maps to 500 units. and one output layer from this 500 units to 10 unit classes, ReLU activation functions and max pooling. Perhaps not max pooling because I didn't explain it. Perhaps we can do just without max pooling because I did not introduce max pooling. So this is already, I don't have my iPad with me because what I would like to do is, I'd like to draw this and I don't want to go back to the screen. So let's just, I will open just a small function notebook, and let's just check what this thing does. So input is 28 by 28, right? So then we have a conv layer, conv1. Conv1 is, we said 5 by 5 filters and 20 output channels. Okay, I'll just go back to one of my slides and show you what this means. Okay, oh no, I'll go back to my original slides, so these ones, and this is a slide I did not show on purpose. So this is what a convolutional layer looks like. And the convolutional layer, my input is an image, and my input can have multiple channels. So for example, in MNIST, I have a single channel because it's a grayscale value as grayscale image. And in MNIST, it's a single channel and 28 rows and 28 columns. And then my convolutional layer will transform this tensor in a new tensor, which has, again, a spatial orientation. So it will have rows and columns, okay? And it has a desired number of channels. So we said in our model, we'll have 20 output channels. This is actually a hyperparameter. This is something we choose. We want to have 20 output channels. What does the model do? For each output channel, it will learn as many filters as there are input channels. It will convolve each input channel with the appropriate filter. It will sum these outputs over the channel outputs, and this will be my output, and it will add a bias. Okay, so if I have 3 input channels and 10 output channels, I will have 30 filters. Okay, so what I do, and this is something I forgot. If this is unclear, oh, there is a question here, Loic. If we train the MLP with data augmentation and all possible translations to Wicked matrices close to convolution matrices, tuplets. So that's an excellent question. Tuplets matrices basically means that if you have a linear layer with a tuplet structured matrix, it corresponds to convolution. So that's an excellent point. And there has been indeed experimental work which does show that this kind of happens, but obviously you don't force that. And this is the reason why we do lots of data augmentation. And until now, so until like 6 months ago, the common kind of community knowledge was that some things you want to force, like through inductive bias, like translation invariance. Translation invariance is something you better forced. And sometimes some things you can force, like rotation invariance, you can create neural networks which are rotation invariance, but it's better to not force it and handle it with data augmentation. But this was empirical knowledge, and you can't really say it in advance. And this shifted, right? And this depends on the data regime. So in this high volume data regime, it turns out that even without with minimal data augmentation, forcing translation invariance is not as good anymore. So unfortunately, this is really something which depends on your tasks, on your data regime. It's not easy, and it's frustrating. It's frustrating. Sometimes people also hide stuff, right? So that's even more frustration. So what Google does, Google said, we use transformers on images, and there are no convolutions at all. What they do is, though, transformers on input images don't make any sense. If you do transformers on input images, then you mean that you take input images with colors, and you calculate attention over colors. Attention on colors doesn't make any sense because the color space is not rich enough to find out where you attend to, right? You have a red pixel, why would you attend to some other red pixel or a blue pixel. It doesn't make any sense. It's not rich enough. So what people did is they calculated first a couple of convolutions, have some descriptor, and then they do transformers on this convolution output. Google wanted to show that they can do that without convolutions. They didn't manage to. So what they did is said, we calculate patches. So each image is decomposed into patches. I have a linear transform on my patch, and I do my transformers into patch space. So what's the problem? This is actually a convolution, right? So if you do a linear transform, which has the same weights over your patches, this means you do a convolution in patch space. And my guess is they just wanted to hide that they do convolutions, and it was discovered, and people were actually pretty angry. So also the difference between convolutions and linear layers are, as you said, Loic, quite close, because one person's convolution is another person's linear layer with constraints on the matrix. Okay, let's go back. Yeah, so, I have 15 more minutes. That should be okay. I'll just want to show you one more slide, which I should have prepared but forgot to do. I'm sorry about that. I'll give you, to work, I'll give you a slide on how convolutions are implemented in PyTorch, else you will have a hard time. So this is a slide deck from my lectures at INSA. So this also shows pretty nicely the difference between a function and a layer in PyTorch. So you have two different types of learning how to do convolutions. So for example, f.convd, so that's a PyTorch function. It takes some tensor f and some kernel h, which is also a tensor, and it just outputs the convolution. So this is really the functional, and you can completely implement a convolutional network in PyTorch by doing this, but this would be strange. So this is really the function which does the work, right? And then conv2d is a functional. This creates a function, and what does it do? It creates a network layer with a couple of parameters, and so the output, the return of this is a functional, which performs the same thing as this guy, and basically internally C here calls f.conv2d. What is the advantage? Well, it hides all the optimization stuff. So it automatically allocates the parameters like the linear layer we saw before. It automatically allocates all these convolution kernels, declares them with the optimizer. When you do the optimizer step, it updates the convolutions. It does all this convolutional magic yourself. But obviously, if you're up to it, you can totally do this with yourself with this conv2d function. And this is what's done internally. So this is what conv2d does. You pass it the number of input channels, the number of output channels, the kernel size. Can be asymmetric. You can do rectangular kernels, for example, 5x3. Kernels can also be space-time, right? If you do video processing, you can do kernels which go over space and time at the same time. I will not explain stride. Padding basically means that you can add zero padded border around your inputs such that the convolutions can have nice border processing. And a couple of other things, bias terms, what kind of padding. So this is really nice. So what I propose we do together is we go back to this thing here, and we talk about how we do this conv2d thing here. What we need is in channels, out channels, kernels. So we define all this, and more importantly, so that's easy to do, but the tricky part for beginners is to find out what does it do to your output tensor? What is the shape of your output tensor? And padding. So any help on this? Input channels, output channels would be easy, right? So input channels is how much? Nobody? Output channels should be easy. 20. That's design, right? We chose to have one. Layla, input channels 1, correct. Input channels because we have a single image. So my input tensor is batch size 21 at 28, 28, right? So I have a single input channel. So in channel is 1, output channel is 20, and what's the design choice here? Why do I say 20 and not 30, 64, 32? That corresponds to the number of features I would like to calculate per pixel, right? Because performing a convolution on my image is mathematically equivalent to calculating a linear function on each pixel where the parameters of this linear function are shared, right? So my output channels is equivalent to the number of hidden units I would have if I had an MLP going over the pixels. So this is basically the same design choice I do when I choose the number of hidden layers in an MLP. My kernel here is, I'll take 5 by 5, it's a little bit large. That's basically how many neighbors do I take into account in my local processing per layer. Padding is the number of padding I will use. I will set it to 2. 2 means 2 rows around my my input tensor. So two rows up, 2 rows down, 2 columns left, 2 columns right. And why would I do this here? That's not a coincidence. Anybody has an idea why would I say 2 and not 1 or 3? Yes. So Baptiste, that's because my kernel here is 5 by 5. So if I center my kernel on my border pixel, then my kernel has 2 border pixels on each side. And this basically means here that I preserve my image size, exactly. So if I don't do that, sorry. If I don't do that, border processing, so for example, if I have a 3 by 3 kernel, then I need a one-dimensional padding here. If I don't do that, I can choose not to basically. Then my my output tensor will shrink because PyTorch will just remove the borders from the calculation. And if I don't do that, if I don't want that, I will set my padding to 2 here. So question: what is the size of my output tensor? So it will be something like batch size times channels times, so we ignore batch size, right? It's transparent. Channels something, Y something, and X something. So how many channels? Not so tricky, right? We just, I'll accelerate a little bit. Well, we defined 20 output channels, so that's 20. How many Y and X? That's not even a trick question. We answered this in 1 minute ago. We preserved image dimension, right? Since I have a 5 by 5 kernel and I used padding, so Y is 28 times 28. If I had set my padding to 0, I would have had 24 by 24 because I would have removed 2 columns at the left side, 2 columns at the right side, 2 rows plus 2 rows. So good. So how many parameters? Oh no, let's make it easy. How many filter kernels? How many filter kernels do I have here? No, not 20, because you have more than 1 filter per output dimension. Remember that you convolve, oh, sorry. We are still at, yeah, sorry, yeah, you're right. We are still at one input dimension. Yes, obviously 20. 20 kernels, because we have one per combination of input and output. We have 20 output dimensions, where we have a single input dimension, so 20. How many parameters? Five by 5, so 25 parameters per kernel times 20, because we have 20 kernels, plus 20 because we have bias terms. I can say bias equals false, and I don't have bias terms. Good, excellent. So what we'll do is we'll change, I'll go back to my code here. So I'll take my, where is it, my logistic regression. I'll copy this. And let's call this LUNET. And so we still need a fully connected layer later on, but first we need a conv1 layer, and we also need later on a conv2 layer. So this is, remember how they are called. So we need to have this up, this function here, conv2d. So that's torch dot n dot conv2d. And we need the information in this order here. So in channels is 1, out channels is 20. We have 5 by 5. When you provide, for example, you can also provide it this way. And you can have rectangular kernels, for example, but that's not the case for us. We'll just say 5. Stride 1. I'll not explain stride. Padding 2. That's it. So we'll have a second one. I'll go back to my second one. Conv2 will say, we said how many layers. I forgot this. What's the, I hope I don't switch too fast. 50 output channels, sorry, 50 output channels. So if you have 50 output channels, for the second one, we'll do, let's say, 5 by 5 kernels as well. Output channels is 50. Input channels would be what? 20. Because input channels of the second layer is the number of output channels of the first. Obviously, because the second layer takes as input the output of the first one. So let's go back. conv2d, 20 input channels, 50 output channels, 5 by 5 matrix, stride 1, padding 2. Okay, so my first layer, let's implement the first ones, okay? So we didn't finish yet because we also need an F2 layer, and the parameters here need to be updated, but let's first, this is just setting up the layers, right? What we now need to do is we need to program the forward pass. The forward pass is basically what we apply to self dot convolution 1 to x. Now something is wrong here. What's wrong here? So I apply conv1 to x. Sounds good. I can also, no, I say just x equals this, and x equals self dot c2 of x. Sounds good. Something is wrong here. Okay, we don't have yet an activation function, and didn't even introduce the concept, unfortunately. I will do, but that's not the only problem. What's the second problem? Anybody sees it? No? This is the thing that's not good. So what does the thing do here? It takes my input tensor and it reshapes it to a flat vector. And that's what we did when we did logistic regression. Remember, we had this image. It's a 2D tensor. And in logistic regression, we did not care about geometric and spatial structure. We took all the pixels and we flattened into the single vector, and this is why I have the view in here. But now we don't do that anymore because we have convolutions, and convolutions just keep the spatial structure. So we remove that. Second thing is, so convolutions directly work on the geometric structure. Second thing is, if we want to have a nonlinear function, then we need to, and I will speed up, I have 3 more minutes. We need to create a nonlinear function, and convolutions are linear functions. If you just stack lots of linear functions, you will get a huge linear function. And for this reason, we can't just put on one end one of the other linear functions. We need to have some, what is called nonlinearity, small activation functions. And we put these in here, torch, and then .relu up of this in here. I have only 2 minutes. I was a little bit too slow. I think I will just load the solution. I will show you what this looks like. It's also f.relu. So conv.1, same as before, same convolutional network. Fully connected 1, fully connected 2, and that's the tricky part. I wanted to show you this. So this looks like magic in here, right? Why do I have this strange thing here? What is the linear part? The linear part here is now an MLP, a linear function, which takes the output of my second convolutional function, okay, and applies a linear matrix to it. Now, the first thing I need to do is, here I have the output of the second convolutional function. I also have max pooling here, which I didn't introduce. Max pooling just means I just reduce the dimension of my image and select roughly every second value in each line, create the maximum. Well, not go into detail. But anyway, after this operation, I have still a spatial tensor, right? Here I want to do a linear combination, a linear layer. So I need to do what I did before for a logistic regression. I need to reshape my output and make it a single vector. Well, obviously a 2D tensor because I have the batch dimension here. So I do the same thing here. The question is, how do I know that I have 4 by 4 by 50 values? Oh, I know it because here I used strides and no padding, strides and no padding. And this means that going in here, we have 1, 28, 28. Here the output is 1, 24, 24, because I did not choose to do padding, so my border pixels are removed. And since I have 5 by 5 kernels, I removed 2 pixels at each border size, so we go from 28 to 24. Max pooling removes, so this goes to 20, 24, 24. Max pooling removes every second pixel on each dimension, so I get 12, 20, 12, 12. I perform a convolution on this. I get, again, no padding. So this means 50, because I have 50 output channels here. 8, 8, right? Because again, no padding, so 4 pixels on each dimension. Max pooling again, 44, 4. So I have a tensor of 50 channels, 4 by 4. And this is the reason here I reshape my tensor to 4 times 4, 50. I actually can do something here which performs these calculations myself. And most people do this, okay? You don't need to do these calculations yourself. I personally don't want to do that, right? Because so much magic can happen in there that I mostly try to convince people to do this calculations themselves. Because if you do an error somewhere, here at the reshape here, you will find it. If too much magic is done, automatically errors go into. So here I have my fully connected layer, which is 4 by 4 by 50 to 500. So I map everything to 500 hidden units. And then I have 500 hidden units to 10 output units, and I'm done. So if I take this and I run it on my CPU, I'll just run the baseline first again, just so that you have an experience in speed, right? So this is the baseline. See the speed? So every line is 100 batches, right? So every line is 5,000 examples. Every time a new line arrives, it's 5,000 examples. And that's easy because the logistic regression just maps pixels to classes. Now, if I take the solution here, it's much slower to train, right? Obviously, that's a MacBook. It's trained on a CPU. If you do the whole thing on a GPU, it will fly. And error goes quickly down, right? So on logistic regression, after 10 epochs, I was at 7, an error of 7. I didn't finish my first epoch yet, and my error is already at 5. So I will stop here. I'll just give you the full thing. If you let it run for 75 epochs, you're at an error of 0.04. Okay, that was a very, very small and tiny introduction. And what I didn't do is we didn't at all talk about generalization, validation, cross-validations, and stuff like that. I'm actually done. I'd happy to take any additional questions if you have one. No questions? Well, good. Thank you, Dan.